Hello, everybody. Let's start our discussion today. Today, we will look at some examples of parallel transport. So, let me remind you what we have been doing and how we define parallel transport, etc. So, first, we have a manifold. So, let me say that we have a manifold. And in this manifold, we are trying to do parallel transport. Now, the manifold, say, if I call it dm, it's a d-dimensional manifold called M. Now, in this manifold, we want to do the parallel transport. The parallel transport is defined along a curve. So first what you have to do is to define a curve. So we choose a curve on this manifold. The curve is parameterized by a single function. The curve is a one-dimensional object, so itself is a manifold and it's parameterized as a single function. Sorry, single parameter. And let us call that lambda. Now, what we will do is we will come to the coordinate description here. We don't need a coordinate so far. Did not need a coordinate so far. But if I have a coordinate, we define a coordinate and say the x alpha are the coordinates, so there are d of them. Then the curve can be now written by four or d functions in this case. And these functions are how the coordinate values changes as a function as with lambda. So we'll call these by the functions will call the by the name of the coordinate. So this is what it is. So this is maybe a wrong notation, not a very good notation, but this is what we mean. So let me emphasize what we mean here. These are four mappings or four functions. This is the parameter, and the values of the coordinate at different lambda. So that is what it means. So once I have this is the curve along which I will parallel transport, and we are will mostly deal with parallel transporting a vector. So let us say that we have a vector now. The vector I can call right like this, but since we have chosen a coordinate, this in the coordinate basis are given by d functions, and these d functions are you call the components of the vectors. So these are, like if you wish, a alpha, and these are functions of the coordinates itself. So now I have a vector which has d functions or d components in a given coordinate basis, and I have a curve which is parameterized by lambda. What I do when I say, what I mean when I say that parallel transporting the vector A along the curve lambda is, so when I say vector A alpha, I mean vector A, just I've written the in terms of its components in that basis along. Now, when I say x alpha lambda, so this is essentially that curve that we are talking about earlier. So to define the curve, I have to specify all components of x. So it's again a set of d functions. Then, so if we parallel transport the vectors along this curve, then their its component must follow a differential equation, which is how we define the parallel transport. So this differential equation is dx mu d lambda, which is the tangent vector to the curve at a point x mu, and then in shorthand, the covariant derivative of a alpha, this equals 0, which one can also write as in full notation dx mu d lambda, and then the covariant derivative is the partial derivative, the usual analysis derivative, and then plus you have equals 0. So remember that the nabla u is essentially a short form of what we have used here. Now, this is the definition of the covariant derivative, essentially what we have talked about so far. Let me just recapitulate. We have a manifold, and in that manifold define a curve by a single parameter lambda, and then we have a vector, and we parallel transport the vector along the curve, or we say that the vector is parallel transporting along the curve if this equation is satisfied. Now, we can choose an arbitrary curve, but now we will be more specific. So this is a specific example, and this is all the class of examples that we'll do today. And there is no particular reason for choosing this specific example, but what happens is that our job becomes easier, the mathematics become easier if we choose this example. That's why we want to choose this, and this is just is going to demonstrate to you something which we will build upon for the next discussion. So what we do is, remember that in the Cartesian case, the general Cartesian case, say 2D, and the manifold is Euclidean, obviously 2D, then we used to draw these things that we have. We say that there is x-axis, which is essentially the value, locus of the points where y equals to 0, and I have a y-axis, which is essentially the locus of the point where x equals to 0. But not only that, we also used to draw this type of equi y lines, or in this case equi x lines, and equi y lines, which are essentially the coordinate lines. Sometimes we call these as coordinate lines. we'll think of a similar concept here where we say for this specific example is that the curve along which we shall do parallel transport are such that the parameter lambda is essentially one of the coordinates, say the coordinate beta. So this line means the parameter is one of the coordinates and all other coordinates remains fixed along the curve. Okay, so these are essentially the coordinate lines, if you wish. See, if I consider this particular line, along this, what happens is that x changes, but the other coordinate, in this case only y, remains fixed. So that is essentially what we are talking about here. Now, if I do that, let's see that what happens to this expression. This expression, which is dx mu d lambda, is now dx beta. What is this? Well, this is a full derivative. This is not a partial derivative, but you see that x now only changes along one of the coordinates. So this, in this particular situation, only it is a partial derivative. So then this becomes delta mu beta. And if I use that, then what happens to my parallel transport equation? My equation of parallel transport becomes delta mu beta grad of mu a alpha, which is essentially you have to change mu by beta, or so to say that in this special case, in the case where the curves are the coordinate lines, parallel transport of a vector along the coordinate lines, which coordinate lines of say x beta, so beta is coordinate lines, so the parallel transport requires equals 0. So it's the covariant derivative of a alpha equals 0 in this particular case. And this is the case that we will deal with today. What will we see? So what are the types of questions that we are asking? So let me list here, or let me write here, what are the questions that we want to see? What do we want to investigate? What we will do is, we will move a vector around in a closed curve. Now, obviously, I will do it by moving it through the coordinate lines. And then I will try to see if its components has changed after coming back to the same position. And compare the vector components at the original position. So I'll start with a point in space like this, and then I will move the vector around a curve, parallel transport. These curves, whenever I move, I always move by the coordinate lines only. And once I come back here, I ask the question. So the initial vector, I'm just drawing for demonstration purposes. This really doesn't make any mean. This doesn't have any meaning. And maybe the final vector is this. So this is the initial vector. This is the final vector. Are they same? Are they different? So that is what we will do. And then next question we will ask is, does the result depend on our choice of the curve? This is very bizarre if it depends on the choice of the curve, but that is what we will check today. Which means that if I go through this curve or go through that curve, will the result be different? Now, you see, we said that we may or may not impose a coordinates, it becomes easier to work out things in coordinate basis. So you can ask the question, does the result depend on the manifold we work on, or the choice of the coordinate? Now, using a set of examples only, it is not possible to generalize whatever we will see, but it is always good to actually see some examples and then try to generalize things later. So we'll take that path. Okay, so let's come with the example 1. And this is a very trivial example, but still we will look at it and we will see that looking at it does have a meaning. So what is the example? So first let us choose. So first we will choose, so we'll go by the same methodology in all the examples. First thing we will choose is a manifold. The manifold is to be Euclidean, and the coordinate system we will choose then, which is to the Cartesian. Now the next thing that I will do is that we will write down the coordinates. So coordinates, and here I will use Roman indices because mostly we are dealing with only spatial part. So what are our coordinates? So I have x1 is essentially x and x2 is y. So my setup looks like this. Just what we drew a little while ago. But let me remind you, this is the line where x equals to 0, and this is the line where y equals to 0. And I can choose another coordinate line where x remains constant. So this is say x equals to L, and another coordinate line where y remains constant, where I say y equals to L. We'll come back to that picture. But let's first write the metric. And metric here is quite trivial. So Gij is diagonal I 1 1. Christoffel symbols, or let me say connections, as we have said, they are also called linear or affine connections. They're all zero because the metric is constant and Christoffel symbols or connections are derivatives of the metric, so these are all zero. The next thing to do is to identify the closed loop, which will go through the coordinate lines. Well, it's quite trivial here. What I will do is let's call this O, P, M, N, M, N, O, P if you wish. So I'll go this way first and then this way and then this way and then come back to O. So OP, in the segment OP, I have lambda equals x1 because that is what is changing, and x2 remains constant and the value of that constant is 0. Then I have the segment PM where lambda equals x2 and x1 remains 0. Sorry, x1 remains L now. And then I have Mn where lambda equals, now when I go from M to N, lambda is changing from M to N and then the coordinate is changing the opposite way. So I should call it minus x1, and here x2 remains fixed at L. And the last one I have is N to O, where lambda is minus x2 and x1 now remain fixed at 0. So these are the 4 curves along which we will like to do parallel transport. But as you may have already guessed, so let me write down what is the parallel transport. What do we mean by the parallel transport? Here, this will require, if my vector is A, this equals to 0. But because all my connections or Christoffel symbols are 0, this also means that, let me write explicitly, A beta del x alpha equals 0. What does it mean? Well, let us go step by step. So if I look at the curve OP or the curve segment OP, there this equation is essentially del A beta. What changes is x1. So this is del x1 equals 0. And you see the x2 is 0 for the entire curve. So this essentially means that A beta is constant. A beta, here beta can be, I should have written not alpha beta but ij, but anyway, so the A beta is constant, where basically you are saying that both the components of the vector remains the same as you move from O to P. As you can imagine, because all the connections are 0, this is what is going to happen for all the other line segments. So in this particular case, we come to the conclusion that if we move a vector around, in the closed loop, A, that the vector never changes, the components never changes, and B is then becomes a corollary of A, that the closed loop difference, let's call that closed loop difference, which is the difference of the vector after it goes around a closed loop, is zero. There is no difference after it goes around the closed loop. And this may be an overstatement here, but you can also see doesn't depend on which loop you have taken. So important point here is that the B and C, that the closed loop difference is zero and it doesn't depend on which loop you have taken. But it's also that in this particular case, that this most trivial example, that there is the components never change. Now let's look at the same manifold, which is the 2D Euclidean manifold. But now let's change the coordinate system and see what that gives us. So 2D polar system we'll work on now. Okay, so now let us do the same game, play the same game again. So what are the coordinates? It's always good to make your hand dirty when you are learning something for the first time. Later you can speed up things when you are quite familiar with stuff. So metric is diagonal. Now 1 and r squared, the metric is no more a function, a constant. So you have not changed the manifold, we have just changed the coordinate system here. What about the connections? This we calculated earlier, so I'll just write down. There are two connections which will survive, and I request you to work this out, and you will at some point, this is kind of just looking at the metric and telling that these are the two connections survives, and it's quite easy to calculate them in a matter of 1 minute. So if you practice enough, then you will see, you'll have that wisdom, and then we'll be able to do that. All right, up to this. Now we have to consider a curve, and it's better to draw the curve first before explain to you what we are going to do. So let me draw the curve. So this is the center of the 2D polar system, and the curve is nothing but a line which is where r remains constant. And as you can see, my center has to be shifted because my drawing was not proper. So this is r0, which is a constant, and I am going around and coming back to that point O. And here you can see that I just need a single coordinate line to describe the curve. The curve we restrict ourselves to is given by R equals capital R naught. Now, how do I parameterize this curve? The parameter or this coordinate line lambda is phi and x1 is constant at R naught. This also has a more interesting consequence, which is that the gammas become constant. So gamma R phi phi, which also if you wish can write as R gamma 1 2 2. This is minus R naught, and gamma phi R phi is nothing but gamma 2 1 2 is 1 by R naught. So these are constant. Okay, now let us move around the curve and see how the two components of the vector changes. So let's do that. We'll work in two parts. In the left side, let's say that del A1, or let me write it as del AR, and what changes is phi. So the derivative is with respect to phi plus gamma R, say alpha phi, that alpha which changes, which is a dummy index, so this equals to 0. And now if you work it out, this is del AR del phi, which is what it is supposed to be always. And I have R and phi, R upstairs, phi downstairs. The only option for alpha to be non-zero is alpha where gamma is non-zero, the Christoffel symbol is non-zero, is that alpha has to be phi. So this becomes gamma R phi phi, and then I have a phi over here, which get me to this differential relation. And let me do one more trick here. You see that all along the curve, AR is only a function of phi. So let me write that here explicitly. AR along the curve is only a function of phi. So there is no point of writing this as a partial derivative. I can just write along the curve. It is good enough for me if I write it this way. And then gamma R phi phi is minus R naught. So this is the first equation that I get is this. It's a coupled equation between R and phi. Let's work out the equation for phi. And I do the same drill. And let me change this to D here itself. I have phi upstairs and phi downstairs, so there is no other chance other than that alpha is R. That's the only thing that will be non-zero. And when alpha equals to R, this equation becomes gamma phi R phi is 1 by R naught. So this is so I get these two equations. You will see why I am writing it this way shortly. We get these two equations. Now let's choose some initial conditions such that I can move the vector around the loop and see what happens later. So let's just ad hocly choose AR as, I'm right with the suffix 1. This doesn't mean any coordinate or anything. This is just a number. And A phi is A2. So let me write it here that these are numbers. These are the values at phi equals 0. Well, the equations here and the equations here tells you that dAr d phi is going to be R naught A2 and dA phi d phi is going to be minus A1 by R naught, again at phi equals 0. Okay, so it's like I got a couple of differential equations. They apparently are first order equations, but I have all these conditions, and the differential equations are such that I also get their derivatives at the phi equals to 0 once I know the values of a's at phi equals to 0. The reason I write the derivatives is that I want to combine these two differential equations. And it's not difficult to see that I can take the second derivative of a with respect to phi, and that will give me minus r naught and then d phi d phi, which we can write from here as again a minus 1 by r naught and then ar, and that's equals to 0, which, so let's call it first equation, that is of r. This essentially means this is a kind of simple harmonic oscillator equation which looks like this. If you look at the other equation, you will surprisingly see it looks exactly the same. Still, let me work it out for you, at least for this particular case. So I get 1 by r naught and then dA1 d phi sorry, dAr d phi, and dAr d phi is nothing but r naught a phi. I'm sorry, this is plus. Equals 0, exactly the same equation, now in phi, a phi. So I have the solutions. So the general solution are, as we all know very well, this AR I can write as, say, capital I, some constant, cos phi plus j sin phi, and a phi will be some k cos phi plus L sin phi. If I use the initial conditions and I'm not working out because you are adult enough to do this by yourself, you will see the solution that I get is AR will come out to be A1 cos phi plus R A2 cos phi, A2 sin phi, sorry, and A phi will come out to be A2 cos phi minus A1 by R naught sin phi. Okay, so it's interesting that the components of the vector changes as you move along the curve, as you move along that circle. I request you to actually plot this component of the vectors as you go along the surface. For example, you can choose the initial vector to be like this, which essentially mean that a1 is 0 and a2 is some value. You can choose it to be 1. And then see what happens to it as it goes around the curve. Definitely it changes as it goes around the curve. But after a complete rotation, and that is of 2 pi, let's see what AR is. So AR, after a complete rotation, phi becomes 2 pi, sine phi becomes 0. So AR is A1, cos phi is 1, and A phi is A2. Exactly where they started with. So though the vector components changes as you go along the curve, as you come back to the original position, they are exactly the same. When the vector components goes around the curve, they changes depending on what curve you are in. How do I say that? Because R0 is sitting over here, which is essentially parameterizing the curve. But when you come back to the original position, it's independent of which curve you are choosing, at least for all these circular curves. So what we have concluded here, so let us go back to the previous conclusion and see. If we move the vector around in the loop, for the Euclidean and Cartesian case, the components never change. That is same here. No, that is not same. The components does changes as it goes around the loop. But B and C remains as it is. The closed loop difference is 0 and doesn't depend on the loop. So what is our conclusion? In the closed loop, the components doesn't change and this result doesn't depend on choice of the curve. Well, we have not done it for an arbitrary curve, of course, but at least for the family of circles, it doesn't depend on that. Now, these two examples are both of the same space, which we called the 2D Euclidean space, and we have an intuitive notion that 2D Euclidean space is not curve. So let's pick up an example where intuitively we know that the space is curved. So this is again 2D. The manifold is the surface of a cylinder. And what do we want as the coordinate? Is the 2D cylindrical coordinate. So let's see what happens there. I will go step by step as we have been always doing. So first we'll write down the coordinates. The coordinates are the x1 coordinate we'll call phi. The phi is the x1 coordinate, and the other, which is x2, is z. Metric. This is obviously diagonal. And interestingly, here the metric is r0 square and 1. Remember, if I want to write down the line element ds square, it will be r0 square d phi square plus z square. So the metric is r0 square 1, which is interesting. because this are all constant, just like we saw for the 2D Cartesian, 2D Euclidean Cartesian coordinates. What about the connections? Well, if the metric is all constant, all the connections are zero. That itself is telling you that whatever parallel transport I want to do around the coordinate curves, it will not change the components of the vector at all. But let us still do it a little bit more systematically. This is the surface of the cylinder. I try to draw that we have axis of the cylinder, and the curve that we'll choose is a curve which is trivially goes around and comes back. So say this is a point O, this is again a circle, it's a circle of radius r naught. So that is the curve of our choice. So let us write the curve. The curve is x1 is the parameter and x2 is fixed at any value, say z0. It's really independent of the value of x2. And I don't really need to don't do anything. I know the Christoffel symbols will 0. So what will happen is just like the case of the Cartesian coordinates in Euclidean space, and it will not change the vectors at all. Now this is interesting. Let me write down the conclusions. The vector components never change any time along the curve. What else? The vector component, which is now becomes a corollary only, are unchanged in a closed loop. I request you to find other loops and try to verify this. It's quite easy. It actually is true for any loop that you choose, even if it is not a coordinate line. And so this is again is also redundant, but still let me write down. The results doesn't depend on of the curve of choice. Now I put an exclamatory mark at the end because this is really surprising. An apparently curved manifold result is just like Euclidean. Well, it's not an Euclidean manifold. I mean, if you you can see that the surface is curved. The surface of the cylinder is curved. It follows a kind of circular thing. But why is it that it shows the exact same result for this particular experiment as that of a 2D cylindrical, 2D Euclidean space? Well, there is one interesting observation here. If I take this and just cut open from here and make the surface of the cylinder flat, it will just look like an Euclidean manifold. So that is something interesting, that if it is cut open and made flat, it looks like an Euclidean manifold, and it has the properties of the Euclidean manifold as long as you are comparing these things of the parallel transport. Okay, so I'll not go any further on the discussion of this particular type of manifold or example here. Let me take up the last example. So long we have not found any evidence that the second and third will be otherwise, which is that the vector component will be unchanged after the closed loop travel, and the result will depend on some parameters of the curve. Now let us find an example, and obviously this example will break all these. That's why this example is there, and it's just one step off from the cylinder. This is 2D surface of the sphere, a surface of a sphere. Not talking about the inside the sphere, only the surface. And this will be polar. I'll not write 2D polar because you may confuse it with the polar coordinates on the two-dimensional Cartesian system. This is a polar coordinate on the surface of the sphere. So it will be clear once I say what are the coordinates. The coordinates x1 is theta and x2 is phi, the two angular coordinates. Metric, let's assume that the radius of the sphere is r0. So the metric Gij is r0 square into diagonal. I just have taken r0 common outside. So 1 and sine square theta. Connections. This I request you to work out. I'll just write it down, and again, once you have done enough exercise, let me tell you that it is quite easy to write this down just looking at the metric. So both of them depend on theta because Gij depends only on theta. Now what is the closed curve that I will choose on the surface of the sphere? Remember that we want the closed curve also to be a coordinate line. So let me draw half of the sphere. And if you remember that if I start measuring from there, this angle is phi, and you measure theta from the vertical axis. So I can have a plane here which has the same theta, which I call theta naught. I just project it like that, so this is, let's call this point P. So what I will do is I will start from P and move around in this curve. And that curve is at a theta equals theta naught. So I can define this curve as lambda is phi, that's a coordinate that changes, and theta remains constant at theta naught. That's my definition. That's the closed curve. Okay, so let's do the parallel transport. Here things are completely non-trivial. So one thing that happens immediately is that the gammas become constant in that along this curve. So this is sine 2 theta naught by 2, and gamma phi theta phi is cot theta naught. Alright, let's see where we can go from here. So parallel transport of the vector A. So let's do for theta component first. Del A theta del phi plus gamma theta is phi, and this, let's start with calling it as, say, I. It will be more appropriate than alpha. This is my equation. And if upstairs there is theta, downstairs there is phi, I can only be phi. So what I get is del A theta del phi plus gamma theta phi phi A phi is 0. Again, at the same logic, A alpha or AI depends only on phi. So I can make this as a total derivative, and this particular connection is minus sine 2 theta naught by 2, and you can write this way, just like we did before. And let us do for del phi plus, now this should be phi, this should be phi, again AI is 0. Upstairs phi, downstairs phi, I can only be r, sorry, not r, but theta. So this implies fine. Again, just like before, we choose initial conditions. These two equations, by the way, looks almost same as the equations that we got for the 2D polar case with Euclidean geometry. The only difference is are the sine theta and cos theta factors. So let us write down the initial conditions first. So phi equals to 0 is the initial condition. We say that a theta is, we call it a1 at phi equals to 0, and a phi we call it a2. And just using these differential equations, dA theta d phi is and this is again at phi equals to 0, so this is also at phi equals to 0. This is sine 2 theta 0 by 2, and a phi was a2 at phi equals to 0, and d phi is minus cot theta 0 a1. So you write down the differential equation again, which I will not do. I will just go and write down the solution directly, because again this is the same exercise, we have done it before. A little bit difference in the differential equation in terms of some constants that you should be able to figure out. So I'll write down the solution directly. That's the solution. The solution looks the following. So a theta, and remember that this we are figuring out as a function of phi. This is a1. Previously we had cos phi, but now because of this two factors over here, sine 2 theta naught and cot theta naught, we will have cos of some alpha phi. I will tell you what is alpha. And then, or let me write this a little bit differently. Let me write the solution first for you, and then we can discuss. Please verify these solutions. And these solutions you have actually already seen in some context, which is absolutely quite related to the context that we are doing here, but I'll not tell you. So you have to figure out, thinking about it, where you have seen these before. These are the solutions where alpha is sine 2 theta naught by 2 and beta is cot theta naught. Now let's see what happens. What happens if I consider, so let's consider two cases. So case 1, clearly that the solutions are different at different values of theta naught. Point 1. Point 2 is that we see as the vector goes around in that circle, it is changing its components. The question is, when it comes back to the same position, that is at phi equals to 2 pi, does it has the same values at phi equals to 0? Let's consider the case where theta 0 is pi by 2, which is essentially the equator. And if theta is pi by 2, cos theta is 0, so which means both alpha and beta are 0. Then what is the solution? A theta at 2 pi is, well, both alpha equals to 0 and beta equals to 0. The second terms in my expression for a theta and a phi doesn't matter anymore, and because alpha and beta are 0, the first terms cos 0 is always 1. So a theta is a1 and a phi at 2 pi is a2, which is essentially the same values from phi equals to 0. So if for the case 1, theta is theta naught pi by 2, which is the case of the equator, the largest circle that you can put in changing theta naught there. This is the case. What about case 2? What is case 2? We choose such that theta naught is pi by 4 instead of pi by 2, which gives me alpha as half and beta as 1. Let's see what happens now. So a theta at 2 pi is what? Well, alpha is half, beta is 1. So alpha times beta is half. So which means that if my phi is 2 pi, so let's write it here. So this is a1 cos of 2 pi by 2 is pi. And then you can see that it will be a2 by 2 sine of pi, but sine of pi is anyway 0, so I'll not write that. What about a phi? A phi is a2 cos pi. Cos pi is minus 1, so this is minus a1 and this is minus a2. Wow, both the components has changed and it's just reversed in sign as your theta naught changes. So what have we learned? What is the conclusion? We see first the vector components changes during the parallel transport. Right? The vector components changes as you parallel transport. This result, obviously, if theta 0 is pi by 2, this is not true, but in general it changes. The closed loop change happens. And here the above result depend on the curve for parallel transport. You see, finally we have come up with an example where all three are true. The components of the vector changes all along the parallel transport. It becomes different after rotating by 2 pi, after full rotation, and this result, how much it will rotate after a full rotation, how much it will change after a full rotation, depends on what is the value of theta naught, which curve you are in. This rotation of the vector, we'll see, you can now, I leave it to you to see that this results to a rotation of the vector. In this case, you can see it's a rotation of a factor of pi. The vector just changes the direction exactly opposite way. So you can think of the direction of the vector changes, which you can write in terms of an angle which you may call phase, this phenomena is essentially related to the geometrical phase in optics. What does it relate to in classical mechanics? I have given you a hint that this will relate to something in classical mechanics that you have already heard, already studied, but I will not tell you that because you have to figure it out. Think about it. What you have learned is that it must be that the surface of a cylinder and the surface of a sphere have different properties. That is because completely different thing happens in these two surfaces. Though intuitively we think both of them are curved surfaces, but there is some fundamental difference between them. One thing that we have just discussed passingly while dealing with the results on the surface of a cylinder is that I can cut the cylinder and then make it flat, and that it becomes just like an 2D Euclidean space, and that may be the reason why the results on the surface of a cylinder matches with the results of the 2D Euclidean space. You may try to do the same thing for a sphere and think about it, but you will never be able to do it. You cannot cut open a sphere or the surface of a sphere and make it flat. It's not possible. So there must be something fundamentally different going on between these surfaces. We'll see what is that fundamental thing and how do we quantify it, what are its properties in the next lecture. Thank you.